Okay, group, this is going to be new content. This is going to be a challenging lesson. I want you to really start this with an open mind and be sure that by the time you're done, you're going to understand a little bit more about trigonometry besides just trig ratios and SOHCAHTOA and sine cosine law. You're going to understand what it means to take the trigonometric ratio of an angle more than 90 degrees. Okay, you can't have a 90-degree right triangle with an obtuse angle in it. So we wrestle with this question, what would it mean, for example, to even calculate sine of 91 degrees, or what if we wanted to calculate the cosine of 145 degrees? Maybe that we wanted to do calculations with the tan of 178 degrees, or even angles that exceed 180. Those have to have mathematical meaning, and certainly some of our calculations with sine and cosine law could possibly involve ratios such as the first two there, because you can have sine and cosine law very much useful for angles more than 90 in an obtuse triangle. So we're going to wrestle with this a little bit. First slide here, you should have your note out. Just fill in some of the blank information, and as the concepts start to come out, if you need a little bit more explanation, here's the time where you're going to be jotting down questions in your notes that you want to ask in class. Okay, so to start out, in order to understand trig ratios for angles that are more than 90, we need to set up a different system that doesn't depend on opposite, adjacent, and hypotenuse anymore, because that's a system that works for a right triangle. Now, some of these angles that we're going to be working with will be acute angles, just to get this new system introduced, but some of the terms we're going to need are on this page. They are initial arm, terminal arm, and angle in standard position. Now the angle in standard position is just the angle that's formed between the initial arm, which is the positive x-axis as indicated there. The terminal arm is where it terminates or ends, and that could be, in this example, quadrant 1 angle. You should have seen in your investigation that there are 4 quadrants on a coordinate grid. The first quadrant is the positive quadrant, where both coordinates are a positive value. Quadrant 2 also exists, and that has different properties. We'll see as we explore obtuse angles, but for now, those are the key terms. The angle in standard position would be formed between the two of them, and this really is the measure of the angle right here. Okay, so the definitions are there. You just have to label the terms on the diagram and draw this simple little coordinate grid with a terminal arm in quadrant 1 and the origin shown with your labels on the axes x and y. Okay, now we want to understand, why do we need a coordinate grid? Okay, so your next page in your handout package is going to answer that question. How do we find trigonometric ratios for a point on a coordinate grid? Now, this initially, when you look at this diagram, there are some things that are familiar about it. It certainly has the look of a right triangle. We have base, we have height, we have what could be called the hypotenuse, but the labels are a little bit different now. Because we're using a point for defining our angle, and this point is on a coordinate grid, the coordinates x and y are going to be important, and that's why we need the axes. So the initial arm, or initial side, as it's shown here in this diagram, would be the x axis, and it would also, for that length along here, it would represent the x coordinate. Okay, that would be the x coordinate of that point. The vertical would be the y coordinate. Okay, and that is shown as our second coordinate for our point. But we also have what we would traditionally call the hypotenuse, is now being referred to as the terminal side or terminal arm, and it's going to be labeled with an R. And as we'll see in the next section, the answer to this next question relates the three variables, x, y, and r. Now I'm just going to, from here, define the sine, the cosine, and the tangent for a point on a coordinate grid. The first one is the sine ratio. Sine we traditionally have known as opposite over hypotenuse, and this definition still works well for a point on a coordinate grid. The only difference is now the opposite is the y value of the point. That's the vertical height, be the vertical coordinate. If you imagine this point moving over onto the y-axis, that length there is of course y. And the hypotenuse now would be the length of the terminal side, and it's being labeled r. Now r there, it's being kind of borrowed from the radius of a circle r, but there's no circle on this diagram, and yet we could imagine perhaps this terminal side being the radius of a circle that would rotate around in our grid. Now that's just an aside, but that's where it comes from, okay? Now the cosine we know to be the adjacent over hypotenuse, and that still works well here for this situation, except now the adjacent side is going to be our x-coordinate, which is along the base of the triangle, and our hypotenuse, again, still the terminal side length, which is r. So we have these two first primary ratios, the sine and the cosine, now being defined as a fraction, which is what sine and cosine are, their ratios, but in terms of the properties of this point, and if necessary, because the hypotenuse is now has its own separate label, we're also going to be using the length of that terminal arm. The last one is tangent. Now, tangent is an interesting one because it uses opposite and adjacent, and it doesn't use the terminal side. And so we're going to find that the ratio for tangent for a point on a coordinate grid is just going to be a lot like slope. It's y over x, which is really why a tangent is very useful for making staircases and making ramps, because tangent ratio is the slope because it takes the vertical horizontal as a ratio. Okay, so those are the primary trigonometric ratios that we're going to now be working with, and these new definitions here are going to be used anytime we want to calculate the trig ratio for a point on a coordinate grid, or if we find ourselves working outside of the first quadrant. And as we'll see in the next page of our handout, how this will be applicable for obtuse angles. Now, we need to answer the second question. We know the coordinates x and y are going to be the point values that are given, but how long is this terminal side? Well, fortunately, as you've seen in the text below, the length of the terminal side is something we can find using right triangle math. The Pythagorean theorem would apply. This is a right triangle, and so the terminal side here works well as our hypotenuse, and therefore the base squared plus the height squared is equal to the hypotenuse squared. And if we wanted to know the length of r, we would add the square of x and the square of y and take the square root. Okay. Now you might at this point have a question that relates to this, which might sound a little bit like, well, sir, why would I need to know the length of r? Well, I'll tell you why. Look at your trigonometric ratios that use r. Sine and cosine, they each depend on the length of the terminal side, r. Tangent is the only ratio where you will not need to know the length of that terminal arm. You can calculate the tangent ratio just by knowing the x and y coordinates of a point on a coordinate grid. Okay? Let's move on. All right, so now what about trigonometric ratios for angles beyond the first quadrant? Okay, so we won't be dealing with angles that go past the second quadrant, but as soon as you pass the 90-degree mark, you're now into obtuse territory. So what about trigonometric ratios for those angles? Well, the first point to make here is that an obtuse angle is an angle greater than 90. In that case, the terminal arm won't be in quadrant 1 as it was before in our first diagram. It will be in quadrant 2. Okay, which means the point will have, as we know with quadrant 2, you've worked with coordinate grids enough to know that points in the second quadrant or in that area are going to have a negative x coordinate, but they'll still have a positive y coordinate because they're above the x-axis. I'm not going to try to estimate what the coordinates of this point here might be, but we know that x will be negative and y will be positive. All right. Now, that's all we really need to know, is that we need to still calculate our ratios as before. Sine is the y over r ratio. And you can always go back to opposite over hypotenuse, and that still works well here. This is still y, that distance there. Hypotenuse still works well at the terminal side in quadrant 2. Makes an angle with the x-axis. Dotted line closes off the third side, and we could still sort of think of r as being like our hypotenuse. Of course, we have to remember that this angle here, this obtuse angle itself, wouldn't naturally have a right triangle that it would be part of. So the right triangle that we need to visualize is the one formed in the second quadrant. Okay, the cosine is x over r. That's going to be using the horizontal length of this right triangle that we've just created, and again, the length of the terminal side. And finally, the tangent ratio will just use the actual coordinates themselves. So again, here with an x and y pair, we can take the ratio of y over x, and that will give us a tangent ratio. So nothing changes when we calculate trigonometric ratios for obtuse angles. We're still going to use our coordinate formula, these three here, depending on which ratio we want to find. Okay, just keeping in mind that now that we're moving into quadrant 2, there's going to be special properties that will develop as a result of the x coordinate being negative. Any ratio that uses the x value will have a negative trigonometric ratio in quadrant 2. And if we go back to our definitions, of course, because cosine uses x and so does tangent, those two in quadrant 2 will have negative trigonometric ratios, and you can test that right now with your calculator. Take an angle more than 90 degrees, evaluate the cosine or the tangent ratio for that angle, and you're going to get a negative number. Now try the sine ratio for an obtuse angle, and you'll find it's still positive. Okay, so some certain properties will develop as a result of moving into quadrant 2. Okay, the next part of your handout wraps up with the look at supplementary angles. Now, supplementary angles are angles that we've seen before, sometimes that we find ourselves needing to calculate an angle outside of a triangle, and we would be finding its supplement if it extends to a straight line. So I've drawn two diagrams here where A and its supplement S are shown. They have some simple properties. They add to 180 degrees. That's the first relationship. Because of that, one angle, the supplement would be the other subtracted from 180. Okay. If one angle is acute, the other has to be obtuse, and vice versa. So A isn't necessarily an acute angle. A is just an angle. S is a supplement. All those four things will always be true, and those two diagrams sort of visualize the two possibilities where A here is an acute angle and S is obtuse, or the opposite where A is obtuse and S is acute. Okay, if you've made it this far in the video, congratulations, you've had the patience to bear with some pretty challenging concepts, and this is new stuff, so be patient with it. We're going to take our time through this, and this is grade 12 math, so you have to be prepared for some content that you haven't seen before in previous math courses, and be also willing to face some challenges that are going to prepare you for college. So persevere through the next part. We're going to look at the relationship between the trigonometric ratio of an angle and its supplement. Okay, so what we're really trying to see is how do supplementary angles compare when we calculate their trigonometric ratio. So for the sine ratio, they're going to be equal. Supplementary angles in quadrants 1 and quadrant 2 are both going to have the same R value. The terminal arm will be the same length, and they'll also have the same Y value. And because of that, the Y over R ratio, which is what sine is equal to, will be equal. And I'll illustrate this with a simple diagram. Okay, on this coordinate grid I've drawn two angles. The first angle is an acute angle 45 degrees, and the second angle would be its supplement, 135. I know that they're supplementary because they add to 180 degrees. And I chose those two by convenience because visually they're very obvious. 45 degrees would be an angle that would be formed when the length of the base, well, let's just use 4 units, is equal to the length of the height for the triangle. They have to have an equal value. In that case, the point at the end of the terminal arm is 4, 4. If I wanted to calculate the length of the terminal side, I'll do that right now. Okay, so this value of R would be the square root of 4 squared plus 4 squared, which would be the root of 32. Now for the sine ratio, I'm just trying to illustrate that the sine of an angle and the sine of its supplement are going to be equal. Sine of an angle, by our new definition, is now the ratio of the y-coordinate of a point on the coordinate grid to the... So we've solved for the value of r using the formula developed before, the square root of x squared plus y squared, so that would give us the root of 32. And we know that the sine ratio, according to our definition for a point on a coordinate grid, is y divided by r. Okay, now that we have that, we could calculate the sine of angle A. The sine of angle A will be the sine of 45. In this case, that is going to be 4 as a y-coordinate divided by root 32. All right, now when we compare that to the sine of its supplement, well, over here we have another point. Okay, I'll label this Q. Now Q has exactly the same vertical height off the x-axis, which is going to be 4 units. Its horizontal distance away from the origin here is going to be -4. So it'll have point -4, 4. Now, when we calculate the length of the terminal arm over here, I'll call it R also because it's the same length. We'll see that, well, if we know this is a right triangle, the same formula applies. Base squared plus height squared equals the length of r squared. We would get the same result because r would be -4 all squared plus 4 squared. And -4 squared is 16 as well, and 4 squared is 16, so we get the same result. R squared equals that, so R would be equal to the root of 32. So we get the same R value, so we have the same Y value, Y coordinate, therefore the sine of S is equal to also Y over R, which is 4 over root 32. Conclusion, sine of S, sine of A are going to be equal. Okay, quadrant 1 and quadrant 2. Now we have a real important point to make, is that there are two possible angles that have the same trigonometric ratio. And that's really important because when we work with the trigonometric ratio in reverse to find an angle, we now have to be aware that there are two possible angles. And that's really important when we're working with triangles. One might represent an acute angle in a triangle, the other might represent an obtuse angle in an obtuse triangle, if you can visualize that. Okay. All right, so now let's move and look back at the cosine ratio. All right, so for the cosine ratio, here they're not going to be equal. As a matter of fact, they're going to be opposite sign. So the cosine ratio will have values that are opposites. If we use, instead of S as the supplementary angle, if we use its form developed here, which is that the supplement is 180 degrees subtract A, then we can write this relationship in two possible ways. We can say that the cos of the angle is equal to the opposite of the cos of the supplement, or we can say that the cos of the angle would be the opposite of the cos of 180 subtract the angle. You may find that you want to maybe work with this more because you can clearly see both angles in the relationship, but either form of that relationship can be useful to solve for the possibly even the value of the angle itself, depending on what we're given. Okay, we may be given the ratio and we're having to solve for the angle. All right, now the reason for that is that these two angles, the supplement A and S, they're going to have equal R values in quadrants 1 and 2, as we already saw with the previous diagram, but opposite X values. So let's go back to our diagram again. Okay, I've cleared out some of the things that have already been calculated for us. Remember that the value of R is equal to the root of 32. I'm just going to keep using the same diagram, same values, just for convenience here. Let's calculate the cosine of angle A. Well, cosine, according to our new definition, we can still try to think of it in terms of adjacent divided by hypotenuse, and that's helpful to reinforce this new ratio, which is horizontal length x divided by the hypotenuse, which now we're replacing with the term terminal arm or terminal side with length r. So cos A equals x over r. What did I say my x coordinate there was? It was 4, and the r was root 32. All right, so interesting. We have actually, for a 45-degree angle anyway, we have the sine and the cosine both having the exact same value. Okay, now what about the cosine of the supplement? Okay, the supplement is capital S, and we have labeled the supplement in red. So if you're kind of wondering, where's the supplement in this diagram? Well, this is it right here. Okay, that's my angle. So my terminal arm for the supplement is here, and this triangle that I want to form in quadrant 2 defines the lengths of y, which again we already labeled, and the lengths of x. Okay, now if we use again our coordinate definition, x divided by r, we now have to put in a different x value because the terminal arm is 4 units to the left of the origin. So that gives it a negative value, root 32, and clearly negative 4 divided by root 32 would be the opposite of 4 divided by root 32. The denominators are both the same, the numerators are opposite values. So whatever that ratio is, they're going to have opposite sign, okay? And the actual value of it would be .707. Okay, so that means this is 0.707 as a ratio, and this is negative 0.707. So cos of an angle, cos of its supplement have opposite signs. Let's go back and look at tangent. Okay, so the last relationship is for the tangent. You're responsible for understanding the relationships for trigonometric ratios of supplementary angles. So this isn't just more content that I'm inventing, but it is actually a course expectation. So I'm presenting the relationships, and I'm trying to give you an understanding of the reasons for it, visually and just simple explanation, but I think the visual is really helpful. So the tangent ratio, also like the cosine, has an opposite sign between the angle A and the angle S. So the supplement has the opposite tangent ratio. Now again, the reason for that is because quadrant 1 and quadrant 2 angles will have the same y value, but the opposite x values. And we've already seen that with cosine. And so there, because the x values are the opposite sign, automatically the ratios are going to be the opposite sign because we've defined the tangent ratio to be y over x. So remember that whenever one of the coordinates changes sign, the tangent ratio will also change sign. And now if they were both to change sign, then the tangent ratio would stay the same. And actually, if we extend into quadrant 3, both y and x are negative, and that would actually give us the same ratio as a quadrant 1 angle. Now, you're not responsible for ratios outside of 180 degrees, but it gives you a little bit of an idea of how you could handle trig ratios for any angle on the coordinate grid between 0 and 360. Okay? All right, so just the explanation for the tangent relationship was given, and then again the diagram, if we were to go back here, we could be able to calculate the tangent of angle A, which is y over x, almost thinking of it like slope, rise over run. The y value is 4, the x value is 4, and you should know that the tan of 45 is 1. And that happens when the height of the triangle and the base of the triangle are equal. Okay, now tan of 135, which is our supplement, would be based on its y coordinate, and x coordinate would be 4 over negative 4, which is negative 1. So they have opposite values. It wouldn't matter really what we used for our terminal arm. It could be a little bit longer, a little bit shorter. If we went to a new location and made it, say, 8 units out and 8 units up, and our terminal arm extended up to here, our point would have coordinates 8, 8, and if we were to go the other side up to a different location, that would be negative 8, 8, and our ratios are still going to be the same. And remember that similar right triangles have the same ratio, so it doesn't matter here where our coordinate grid is located on, or where our point is located on that terminal arm, whether it be here or anywhere along there. For a fixed angle, say 45 degrees, the ratio will always be 1. For its supplement, again, regardless of the size of the triangle, the ratio will be the opposite. Okay, that's all I'm going to go through at this point. It's a fairly long video, but I've got the concepts out. I'm going to prepare a part 2 video with some solutions solved, which you can watch at a later date.